Welcome to the UART interface course of the HT8 MCU basic tutorial. This course will take you through the UART interface of the HT8 MCU from 6 parts, which are the UART interface introduction, UART interface structure, UART register configuration, UART independent interrupt, application examples, and considerations. UART interface introduction. What is a UART interface? The UART interface is an asynchronous, full duplex, serial data transmitter, which is usually used in one-to-one communication, such as to drive a Bluetooth module or a Wi-Fi module, or to work with an external serial port module to print the debugging information. For more details, please refer to the HT8 MCU UART application note on Holtec's official website. Asynchronous means no synchronous clock signal between the receiver and transmitter. Full duplex means to allow synchronous bidirectional data transfer between two devices. And serial means to use one data line to transmit data bit by bit in sequence. Now let's learn about how to connect the communication devices. When connecting two devices, the UART transmitter pin TX of one device is connected to the UART receiver pin RX of the other device, to form a communication bridge. And both devices need to be co-grounded. How does the UART interface communicate? Firstly, we'll analyze the communicate protocol format. In UART communication, the signal line remains high when there is no data transmission, which indicates that the communication line is idle. When the data is ready to be sent, the transmitter first pulls the signal line from high to low and holds it for a 1-bit time to notify the receiver that the data transfer is about to begin. The start bit is followed by the data bits. A high level indicates logic 1 and a low level indicates logic 0. Data transfer starts with the least significant bit first, the higher bits behind. Taking the ASCII code hex 44 of the character D as an example, the LSB sequence is shown in the figure. The UART provides a parity bit for error detection. For the odd parity type, the total number of logic 1 in the data bits and parity bit should be odd. For the even parity type, the total number of logic 1 in the data bits and parity bit should be even. For example, the odd parity type is used here, because the number of logic 1 in the data bit is even, so the parity bit is set to 1 so that the total number of logic 1 is odd. Finally, there is a stop bit, which is usually a high level that lasts for a 1-bit or 2-bit time, and is used to notify the receiver that the data transfer is complete. Then the signal line returns to idle. The HT66F3195 supports two UART transfer formats, which are the 9-bit transfer format and 8-bit transfer format. For the 9-bit transfer format, the data has up to 9 bits, among which the MSB can be flexibly configured as the bit 8 of data, parity bit, or address bit. The 8-bit transfer format is similar to the 9-bit transfer format, except that the number of data bits is different. The final point of this part is about data transfer speed. The UART data transfer speed is determined by the baud rate, which equals to the number of binary bits transferred per second. The commonly used baud rates are 4,800, 9,600, 19,200, and 115,200. The greater the baud rate, the faster the UART data transfer speed. In order to ensure reliable data transfer, both transmitter and receiver must agree on the same data transfer format and data transfer speed. UART interface structure. The UART interface is composed of the transmitter, receiver, and baud rate generator. The clock source of the baud rate generator comes from a high-frequency clock. The transmitter shift register, TSR, and receiver shift register, RSR, have no physical address, therefore users cannot directly access them. Actually, when two MCUs communicate with each other, the data transmitter needs to write the data to the TXR, RXR register. Then the data is transferred to the transmitter shift register, TSR. Under the control of the baud rate generator, the data in the transmitter shift register TSR is sent out bit by bit through the TX pin, in the order of low bits first and high bits last. For the data receiver, the data is received from the RX pin and shifted into the receiver shift register RSR. When the receiver shift register RSR is full, the data is first transferred to the buffer, then to the TXR, RXR register. Users can read the received data from the TXR, RXR register to complete the reception. Note that the buffer and the TXR, RXR register form a 2-byte FIFO, where 2 bytes can be held while a third byte can continue to be received. UART register configuration. For the HT66F3195, its TX and RX pins are pin shared with PC0 and PC1 respectively. It is required to first use the related pin shared control register to set PC0 pin function to TX and PC1 to RX, before further UART configuration. Pin configuration will be introduced in a subsequent course. The TXR, RXR is the data register, which is used to store the data to be sent on the TX pin, or the data received on the RX pin. In the HT66F3195, the UART data format is determined by the UCR1 register. The UART bit is the UART function enable bit, which controls the UART module on or off. The BNO bit is used to set the data transfer length. If the BNO bit is 0, the data transfer length is 8-bit. If the BNO bit is 1, the data transfer length is 9-bit. In this case, the RX 8-bit is used to receive the 9th bit of the data, and the TX 8-bit is used to transmit the 9th bit of the data. PREN is the parity function enable bit, PRT is the parity type selection bit. The STOPS bit is used to set the number of stop bits. The TXBRK is the break character transmission control bit. The UCR2 is the second control register of the UART, which is used to control the transmitter, receiver, and various UART interrupt sources. When the UART bit is set to 1, the UART function is enabled. The TX and RX pins are further controlled by the TXEN and RXEN bits respectively. TXEN is the UART transmitter enable bit, and RXEN is the UART receiver enable bit. The BRGH bit determines whether the baud rate generator is in high-speed or low-speed mode. ADDEN is the address detect enable bit. When this bit is set to 1, the address detect function is enabled. The WAKE bit is used to control whether an RX pin falling edge wakes up the UART function. RIE is the receiver interrupt enable bit. TIIE is the transmitter idle interrupt enable bit. And TEIE is the transmitter empty interrupt enable bit. The USR register is the UART status register. PERR is the parity error flag. NF is the noise error flag. FERR is the framing error flag. And OERR is the overrun error flag, which indicates whether the receiver buffer overruns. RIDLE is the receiver status flag. RXIF is the receiver data register status flag. TIDLE is the data transmission complete flag. And TXIF is the transmitter data register empty flag. Now think about how to get a baud rate of 9600. In the HT66F3195, the baud rate is determined by the BRG register, together with the BRH bit in the UART register. The BRGH bit determines whether the baud rate generator works in high-speed or low-speed mode, and thus determines the choice of calculation formula. The N in the formula refers to the BRG register value. If we set the baud rate generator to work in high-speed mode, let's calculate the BRG register value so as to get a target baud rate of 9600. According to the formula, we can get an N value of 51.0833. Take the nearest integer 51, convert it to a hexadecimal value of hex 33, then store it into the BGR register. Then we calculate the error between the actual baud rate and the selected baud rate, which is 0.16%. It should be noted that the smaller the error between the actual baud rate and the selected baud rate, the smaller the bit error rate. Let's take a look at what is the allowable error range for the baud rate. Each byte sent by the serial port has a start bit for synchronization, so the error will only be accumulated in one byte, and the allowable limit error is 0.5 bits when the last bit is sampled. Look at the calculation example, which is based on one start bit, 8 data bits and one stop bit. The maximum allowable frequency error between two ICs is 5%, and the allowable error range for each IC is plus or minus 2.5%. It is important to note that the HIRC error will also affect the actual baud rate value. Please calculate the error according to the datasheet. How to initialize the UART? For example, the data format is 8 data bits, no parity bit and one stop bit. The baud rate is 9600. The initialization process is as follows. First, set the baud rate to 9600. In the HT66F3195, the baud rate is determined by the BRG register, together with the BRGH bit in the UART register. Here we set the baud rate generator to work in high-speed mode, and set the BRG register according to the target baud rate. Then, set the UART data format, that is 8 data bits, no parity bit, one stop bit. Finally, enable the UART function, transmitter and receiver. UART independent interrupt. According to the datasheet, the UART interrupt is an independent interrupt. So what conditions will trigger a UART interrupt? First, the data reception is completed. Second, the data transmission is completed. Third, the receiver overruns. Fourth, the data in the TXR/RXR register has been shifted to the transmitter shift register TSR, which means the transmitter is empty. Fifth, the address detection is enabled and an address is received. Sixth, an RX pin falling edge wake-up occurs. Then what is role of the UART independent interrupt? During data transmission, the CPU does not have to wait and can handle other tasks to speed up the operation. Here is a UART independent interrupt example. First, define the interrupt service subroutine name. Then look up the interrupt address. An independent interrupt corresponds to an unique interrupt event. After the program enters the interrupt, the subroutine can handle the interrupt event. Application examples. Let's take the data format of 8 data bits, no parity bit and one stop bit as an example, to learn about how does the UART transmit data. We need to first wait for the UART transmitter to be idle. This is to ensure the previous data transmission has completed, so as to avoid data conflict and error. Then write the data to be transmitted to the TXR/RXR register. Finally, we need to wait for data transmission to complete. Now move on to learn about how does the UART receive data, which is also based on the data format of 8 data bits, no parity bit and 1 stop bit. Execute receiver error detection to determine whether a parity error, noise error, framing error, or overrun error occurs. If an error occurs, read the USR register first and then the TXR/RXR register, clearing the error flag to 0. If the data is successfully received, read the USR register first, then read the received data from the TXR/RXR register. Here is a data reception program example. First, execute the data receiving error detection, including parity error, noise error, framing error, and overrun error detection. If an error occurs, you can clear the RXIF flag and error flag by reading the USR register first, then the TXR/RXR register. If no error occurs and the data is received successfully, read the USR register first, then read data from the TXR/RXR register. Since the UART receiver register of this MCU is a 2-byte FIFO receiver buffer, which can receive 2 bytes of data, if there is no new data in the TXR/RXR register, the above 2 steps will clear the RXIF flag. If there is new data, the RXIF flag is still in the set state, then the received data can be read again, and the RXIF will be cleared to 0. Considerations. If the UART clock source FH is turned off in the normal operating mode, or if the MCU enters the idle or sleep mode, the UART data transmission and reception will stop. If an RX pin falling edge occurs, a UART interrupt will be generated to restore the UART transmission and reception functions. The RX pin falling edge wake-up interrupt requires the following conditions. The high-speed clock is turned off, and the WAKE, UARTEN, RXEN, RIE, UARTE, and EMI bits are all set high. Note that it takes certain system clock cycles after a wake-up before normal MCU resumes. During this period, the data on the RX pin will be ignored. How to avoid the problem of data reception error due to slow vibration of crystal oscillator when waking up from the sleep state. If the MCU uses a crystal oscillator as the main frequency for sleep, it is recommended to send a useless data to wake up the MCU first, before resuming normal communication. Course summary. In this course, we have learned the UART communication protocol, interface structure, register configuration, interrupt mechanism, and UART transmission and reception. I believe that you have a certain understanding of the HT8 MCU UART interface through the learning in this course. Holtec has a professional service team to assist in development design and after-sales service. Please feel free to contact our business departments for more detailed product information and consultation services.